All right, great. So I am very excited to introduce Greg Nemet. So he's a professor. Oh, actually, I was going to ask you this, how to pronounce it, at the Lafayette
Yeah.
School of Public Affairs at University of Wisconsin-Madison, where he teaches courses in policy analysis, energy systems, and international environmental policy. He got his PhD from the Energy and Resources Group, ERG, at University of California, Berkeley, and a bachelor's degree in geography and economics from Dartmouth College. He recently published a really fantastic book that I recommend for everyone, How Solar Energy Became Cheap. It's a model for low carbon innovation. It's a really awesome study. He's an expert on energy technology innovation. And then just from a personal perspective, so I first met Greg when he was still a PhD student at Berkeley. We connected and collaborated on a paper that was published in 2009, looking at how a combination of subsidies and research and development investment would impact the development of purely organic solar cells. It was a really fantastic and successful collaboration. So we kept going, we continued, and we worked together on a project on carbon capture. And so I have to say, Greg is one of my favorite collaborators, as well as a really impressive researcher. And I'm very excited today to hear about, Greg, what you have to say about another batch of climate technology, some of which I'm not quite as familiar with where they are. So I'm looking forward to this talk. So please welcome Greg Nemet.
Great. Thank you. And thanks, Erin, for that kind introduction. And also, yeah, what a pleasure it's been to be able to collaborate over, I think it's about 15 years now. So that's been fun. Yeah, so here are some thoughts I put together that is possibly a paper, or at some point you could go deeper and do like a longer paper or a book on it. But the idea is, how do we kind of set up a set of policies to catalyze innovation to address climate change? And this is kind of pulling together a lot of different parts of innovation. I've been working on different technologies, as Aaron mentioned. And maybe I'll just start with I'll just mention these icons at the bottom here. And I just put these on here because that's what this work is about. But I think that's a lot of my research is kind of focused on these interactions between, if the light bulb is innovation and the Capitol dome there is policy, is how policy can stimulate innovation, and that there can be a feedback too, whereas innovation happens and say performance improves or reliability is established or costs fall, that might make policies politically feasible, that weren't feasible in the past because they were too expensive. So sometimes you might think of a carbon price might work that way. So it's a bidirectional causal relationship between policy and innovation, the light bulb. And then on the right, the idea is that is for environment and climate. So here's kind of the overall thesis that I'm kind of developing with these ideas I'll talk about today, is that climate policy requires a comprehensive, so many policies, many aspects, inclusive, so not just talking about maximizing GDP or per capita GDP or social surplus or whatever it is, but that there's something about the distributional effects that are crucial, and that it's dynamic, and that it's not just about what happens in 2022 or even next year, but there's this ideas of a strategy, a sequence, and that some of these things take a while to play out, and we should design our policy with that in mind. And that all of that, comprehensive, inclusive, and dynamic, is meant to stimulate the innovation and accelerating the adoption of low carbon technologies. So that's kind of the thesis that I'm trying to pull together with the slides I'll talk about next, but that's kind of the bottom line point I'm trying to make today. Okay, so that's the first part. And the other part is to talk about putting these dynamic technologies at the center. And I think, I don't know, maybe for a lot of us that, that work in this area, I know Anna's work is on this and Aaron's work is on this, that maybe this is kind of obvious that that's where we want to focus. But I realize that a lot of people that are very passionate and very steeped in climate change, don't think about technology as kind of the core of the solution, or innovation as kind of something that we would think policy could play a role in. That's kind of something that happens that we might need to actually control and maybe limit it so it doesn't make climate change worse. So I guess, and I mean, I say that with, having spent the last couple of years doing a lot of work with the Intergovernmental Panel on Climate Change, and I very much would need to make this point in that forum, because the idea of technologies are often seen as problematic and contributors to the problem rather than as potential solutions. So I will kind of make the pitch why they're important. So putting dynamic low carbon technologies at the center. And when I say dynamic, I'm talking about technologies that are changing, that are improving, that are maybe getting more efficient or more reliable, or scaling up, or getting adopted, or costs are coming down. So first is that we've seen progress in low carbon technologies. And then if we combine the low carbon technologies with some enabling general purpose technologies like digitalization, so communications, information technology, that creates new possibilities. There's also work coming out that seems to show that smaller scale technologies, for a variety of reasons, and some of which aren't like well explained, seem to get adopted more quickly and improve more quickly. And it could actually be that smaller scale technologies are more scalable. So smaller unit scale is more able to do something big on the climate. Okay, so that's the first assertion. Second is that this progress makes this low carbon transition more feasible and more affordable. So it's a little bit like that link I talked about at the beginning, that these technologies are enabling policies that in the past would have been considered too expensive or not enough support for. So that now, and this is something we weren't really talking about 10 years ago, at least not governments making plans to do this, that we might peak emissions soon, that we might rapidly decline, and that's now something that people talk about as realistic and that governments have plans for. And that was not true 10 years ago. And that some key dynamic technologies can do, maybe not all, but could possibly do a lot of the work to get to zero. And that third, even though we have these technologies making progress and enabling things, we still need policy, and for a few different reasons. We've got this pollution externality, so the greenhouse gases in the atmosphere is the public goods problem. We've got knowledge spillovers, that's kind of a positive externality. So we have too little investment of knowledge because it's too hard for people to fully capture it. So that needs policy too. And then if we think of an innovation systems perspective, that's where people talk about functions of innovation, and that needs policy to support it so that expectations go in the right direction, and that resources are mobilized, and that people are playing important roles that they need to in the innovation system. So for all those reasons, we need policy. And then related to that, if we look at models, especially models that are meant to be kind of comprehensive and talk about the energy system and the climate system together, they are often they're complicated models. And so they want to be rooted in real data, in peer-reviewed, reliable data. And one of the problems with doing that is having that emphasis is that you end up being satisfied with data that's outdated because it's peer-reviewed, it's well-established, you got all the kinks worked out, but it might be from 2005, or it might be from 2015. And for some technologies like electric vehicles, using data about performance or cost from 2015, and then thinking about how that applies to 2022 or 2030 starts to lead you to conclusions that are different than if you used a set of policies or models that anticipate how technology changes. And so finally, the point here is that we should design policy with technology dynamics in mind. And this means we need a comprehensive policy mix. Some people might call it industrial policy. And a lot of where the constraint might be on that is having capacity in government to access information, to make good decisions, using that information to work with the private sector. But it asks a lot more of government players and agencies than we have at least in the last 40 years or so. So that's the overall argument. We just put a few other elements up here. These are kind of my own premises that Urgency is important in terms of dealing with climate change, and accelerating adoption is also important. We probably need multiple policies in a strategic sequence, that government may need to engage deeply in innovation, and that we have to think about these aspects such as social acceptance and distributional impacts and inclusivity in addition to technology, because technology has impacts on those. We should also think about local learning. So what happens not just in this global system, but what happens at the local level, and how these maybe globally derived technologies can integrate with local systems, with local expertise and local behavior. And that policy probably needs to be adaptive, that we might learn from experiments, maybe on small scale, maybe temporarily, maybe in certain jurisdictions. And the ones that work, or ones that have appealing attributes, we can scale up and adopt more broadly. And that seems to make a lot of sense from kind of a scientific perspective, but from a policymaking perspective, this idea of experimentation is often not as well received, because if a policy doesn't work, it might give you new information, which from this perspective is actually really helpful, but from a political perspective might be seen as a failure. Okay, and I think I've mentioned this zero target a couple of times. So this is just some kind of summary information about where we are today in terms of CO2. So we're getting pretty close to 40 billion tons of CO2 going into the atmosphere every year. And that if we wanted to be on a trajectory for 2 degrees, which is what we agreed on in Paris in December 2015, that we need to peak pretty soon, if not already, and start declining rapidly so that we get to net zero emissions by in the 2060s. And if we wanted to get to 1.5 degrees, then that crossover has to be around 2050. And that's also something that we agreed on in Paris, that we make efforts to limit warming to 1.5 degrees. And then just so everyone understands here, so what we, on the left side of that, before 2015, or before where we are today, 2022, is just about emissions. But you can see starting in the 2030s, you start to have this below the line number. And these are technology broadly, of removing CO2 that's already in the atmosphere. And that's sometimes called carbon dioxide removal, or it's sometimes also called negative emissions. And so when we say net, that just means that what we're putting into the atmosphere, and we subtract the negative emissions from that, and that sum has to get to zero by, in this case, 2065 or so. So it does mean talking about technologies to remove CO2 that's already been there. So that's just an important part of with thinking about what the target is. We need to get to zero, but we might have to go negative to do that. And here's just a slide that I put up in my energy class that I think it's just important to realize that this is not simple to do for 3 reasons. One, everybody wants energy that's cheap, clean, and reliable. But if we think about what we prioritize, people come to different conclusions. So, people that are concerned about affordability might really want cheap energy. People concerned about air pollution, like asthma in that picture there, or about climate change, are really focus on the clean. And people that are concerned about security, like people in Europe right now, might think about reliability as the number one thing that they want. So I think we all would want a system that's cheap, clean, and reliable. But until we have that option, we disagree about what we want from the energy system in terms of which of these 3 goals we prioritize. The other difficulty with energy transitions, and a transition like getting to zero, to connect it to the slide before, is that if we look in the past, transitions took a long time to happen. So there have been 2 transitions in the last 150 years. One was from an energy system primarily based on wood to one primarily where coal was king, like 100 years ago, to one post-World War II, where oil was the dominant technology, and then possibly to one in the future where we talk about zero emissions being the transition or the main energy carrier. But remember, we have to get to zero by 2050, 2060. And so if we're in 2022 today, we're only talking about 3 or 4 decades, not the 7 decades that it took in the past. So that's a reason why 2050 and 2060 are not the distant future. Those are actually kind of a rush to get those if we look at what's happened in the past. And then the other part of this, and the reason we talk about negative emissions, and this is really important for climate change because it's so different from things we've done successfully in the past, like clean up acid rain or clean up NOx emissions and particulates in cities, which do things like create asthma and create health impacts. If, when it rains, most of that pollutant washes out of the air. It's not there after a few weeks. With CO2, most of it stays in the atmosphere for more than 100 years, some for much longer than that. And so you don't get this kind of fresh start. And so there's this lag in the system. So that, again, speaks to a need for urgency, despite the slow-moving system. Because the system is slow-moving, we need to be urgent. So despite that, and I started making this list of reasons for optimism about this problem, because I think my students were getting the points on the slide before only too well and just felt discouraged about the whole thing. So here's my list that I've built up over the years. And I think over time I've become more optimistic because 1, this list has gotten longer. 2, each of the items on this list I find more credible. And then 3, when I talk to other people, they have items I don't even think about here that have become more important. Like this number 8, young adults, has been on the list for 10 years since I started it, but it's only been in the last 3 years that that's played a major role in affecting policy. And that was something I think people kind of expected should happen or would happen, but never seemed to really happen until the Fridays for the Future movement started in 2018, 2019. So there's really been some changes here, but the one I'll talk about today is on number 1, because 1, I think it's one of the most important reasons for optimism, and 2, it underpins a lot of the others. So, one reason we have the Paris Agreement and we have this idea to get to 2 degrees and 1.5 is it looks more feasible than it did 10 years ago, in part because of number 1, technology improving. Okay, so and these slides are really just to kind of substantiate some of the points I made in the first couple of bullet list slides. So the first one is that we are starting to think of rapidly decarbonizing the economy, like getting to net zero, feasible. And here's one example here. This is from a business publication, Bloomberg News, about renewables are now making the cost of getting to zero cheaper than it was before, and on the order of $10 trillion. So these are big, substantial changes. And we can think about, there's been lots of subsidies to improve renewables and get the costs to come down. And if you add them all together, it's like on the order of $500 billion. That's a huge amount of spending on renewables, but that's $500 billion compared to the 10 trillion benefit. So that's partly what we're starting to see happen. And again, this isn't an advocacy group. This is a business publication. And then we're starting to see studies that show getting to zero in feasible ways and even nearer term. So if we just look at electricity, so that doesn't include all of energy, but just electricity, there's a study from UC Berkeley that said we could get to 90% clean electricity in the US in just 15 years and you can see the different parts that play a role. So wind is the biggest one. And this is a wind seminar here. That's the biggest source of clean electricity in this scenario for 2035. So near term, it's like less than 15 years now to get to 90% clean. Okay, and then other studies have come out along those lines too. Yeah, and then let me just put together some empirical results here that also inform how we accomplish that white line on the bottom graph there of getting to zero. So first is, and here's some evidence of technology improving. I think one thing I find encouraging is it's not just in one technology. So solar is one that I've worked on a lot, and Aaron and I collaborated on quite a few years ago, and that's been a dramatic change, the price going way down, actually a factor of 10,000 over the long period of time. Wind has been on not quite as steep a trajectory, but also has steadily declined in cost, and especially offshore wind. That's been the dramatic change in the last 10 years. And so that's also contributing. And you can see why that Berkeley study I showed before had lots of wind on it. And then the shorter curve, because it just hasn't been commercialized as long, is lithium ion battery packs here. And you can see the slope of that line is similar to what wind was in its early years and similar to what solar's been over a long period of time. And batteries are going down in cost for a lot of the same reasons that solar has. A modular technology, taking advantage of previous technology or previous applications like laptops and smartphones, stringing together lots and lots of exactly the same thing that you could assemble quite cheaply, using a dominant design, like the same material over and over that becomes proven. People are familiar using it. Supply chain develops specialized equipment for manufacturing it. All the things that made solar come down in cost look very similar for batteries as well. So we've got multiple technologies, and we've got others as well, as I'll mention as well. Okay, and then for the solar, I'll just, Aaron mentioned my book from a couple of years ago. I'll just summarize it in a minute here, is that we have this factor of 10,000 cost reduction over 70 years. And if you put the cost data on a log scale here, so that's the factor of 10,000 here, we had the first commercial application was on a satellite license from Bell Labs in 1958. And the units here are dollars per megawatt hour. So megawatt hour is average electricity consumption for a residential single family home in the US. So it's like a monthly electricity bill. So if you did that with the satellites from 1958, you'd be paying $300,000 a month for your electricity. But as a result of all these changes, now you'd be paying something like, if you're in the desert doing it in a large scale, $20 a month. And if you're doing it in a residential household, something like $50 or $60. So dramatic cost reductions. The other thing you can see from the kind of the flags on these little circles here is that no one country did it. Every country that had a lead on policy, every firm that was the biggest firm in the world for producing solar, never had the lead for more than a few years. And each of them relinquished that lead to some new company or some new country doing things. And the main thesis that comes out of the book is that each of these countries, there's 5 key countries here, played an important role in adding something distinct from what they had in their innovation system. So the US did a lot of R&D in the 50s through the 70s. The Japanese also picked up on that R&D, but started to sell solar in niche markets like consumer electronics, like calculators and watches that were tiny and didn't make any difference in terms of energy supply, but they enabled the technology to scale up and become reliable. And they got big companies interested in it, like Sharp, that eventually became the biggest producer of solar in the world. And then you started to have policies that were working on the demand side, starting in the 1980s in California with the ISO, the Interim Standard Offer Contract number 4, which guaranteed a certain price for 10 years for small scale energy generation. And most of that was wind. And you had about, it was $1 to $2 billion of Wall Street money that went into California wind turbines, wind farms in the 1980s. And a lot of them were turbines that were built in Denmark and then installed in 3 mountain passes in California. But it really showed that you could use policy to stimulate private investment, and that could lead to innovation, like big improvements in capacity factors, for example, and cost reductions in those early wind turbines. The Japanese had the rooftop program, which was a subsidy program for consumers to have their own production of electricity. It showed that people were willing to pay money, especially if the government paid like half of it. And then finally, the Germans with the EEG in the late 1990s had their own subsidy program that created this big demand for electricity and a demand for solar panels. And China met that demand, and the company there called Suntech became the biggest solar producer in the world. And eventually China started its own feed-in tariff and became not only the biggest solar producer of solar panels in the world, but the biggest consumer of solar panels in the world in 2013 after their feed-in tariff started. So lots of different countries played a role. And it was this global innovation system where people in countries moved around, ideas were exchanged, money flowed from one country to another, machines went from one country to another. And I think the anecdote to me that encapsulates this global flow the best was, so I talked to the founder of Suntech. So he founded the largest Chinese solar company in the 2000s, and this was in 2000, 2001. And the way it all came together was that it was US pension funds, so retirees in the US investing their pension money. Some of that goes into stock market. And so this Chinese company, Suntech, had an initial public offering in New York. And so $300 million goes from pension funds in the US to this Chinese solar company. The Chinese solar company then uses a lot of that money to upscale their factory. And they do that by buying equipment from Germany, from Switzerland, from Italy, and from the US. They bring those machines back to China and produce solar panels with them. And then the market who's going to buy those solar panels was Germany because of that feed-in tariff that Germany had. And so the solar panels go to Germany then, and eventually the German policy ends because there's election. And so the market moves to Spain and then to California and eventually to China itself. So it's really this global flow of knowledge that moves around that led to this cost reductions that we saw. So that's an important part of how the story works here, but the global flows are really just something that was so crucial here. Here's another thing that comes out of some of the empirical work is this idea of sometimes called modular technologies or small scale technologies or granular technologies. And the data seem to show that smaller improves more quickly. And the metric here for improvement is learning rate. So a learning rate is how much the costs go down when you double the production of a technology, double the capacity of it. And you can see that in the middle here looks like about 0.2. So a 20% cost reduction if you double production of a technology. But you can see lower rates on the right-hand side where we have a gigawatt. So that's like the scale of a nuclear reactor or a large coal power plant. And on the left-hand side, we have stuff that's a watt or less than a watt. So maybe it's like the laser in a CD player or something like that, or an LED, small LED light. So smaller seems to improve more quickly across a wide variety of technologies. Lots of dispersion here. So there's other factors that we need to understand and take into account, but there is something about smaller improving faster. The other thing we see was smaller, and it's a similar horizontal axis, just instead of electric capacity, it's in dollars. But similarly, in terms of orders of magnitude here, is that as you get to more expensive technology, the time it takes to go from 10% adoption to 90% of where it eventually gets higher as you go to the right. And again, there's quite a bit of dispersion, and the R squared you can see is pretty low, but there is something to that slope of the line that larger scale technologies just seem to move slower than small scale do. And so it starts to prompt like, well, what other factors would explain it? What explains that dispersion? But also, what's the causal mechanism for why smaller should go faster? And I think there's multiple, but one of them is probably just the number of iterations you have. And this is one where it's not about dollars, it's not about gigawatts, it's just how many things do you make. And you can see this is also logarithmic scale on the vertical now and looking at it over time. But if you look, in the history of nuclear power industry, we've built less than 1,000 nuclear reactors. In carbon capture, we've built about 24 carbon capture facilities. We've built about 3 million wind turbines, and we're getting close to 10 million electric vehicles on the road. And we've produced between probably now about 3 billion solar panels. And so if you just think of, the difference between nuclear and solar, it's like a factor of 1 million more opportunities to learn, to introduce some new production technology, to alter how manufacturing happens, or to add some new material or new design or experiment, or just train employees about how to do their task. And there's just so many chances to change things when you have so many more iterations. So that seems to be a big part of why small is both faster to get adopted and faster to fall in costs. Okay, so here's one outcome of that work is that it may turn out that small scale technologies, small unit scale, like a wind turbine or solar panel, may turn out to be more scalable, like make a bigger contribution to energy supply or climate change mitigation than large ones. And I think that's really an idea that has a lot of acceptance now, or at least a lot of interest in developing further. And when I was in grad school, was the reason that you wouldn't really ever take wind seriously or solar seriously is just because they were too small, and that meant you weren't really appreciating how big the energy system is or how big the climate problem is. But actually may turn out that smaller allows things to happen more quickly and thus get bigger than large ones. Okay, so some of those, putting some of those things together, one of the implications is perhaps we should focus our effort on a set of dynamic technologies, ones that are changing, and maybe that's we want small unit size, that we maybe focus on iterative improvement, so things where you have all these chances to improve it, and that local system integration is an important part of that as well. So yeah, let me just kind of review some of the technologies that might play a role here. So we've talked about this top 3. Then there's emerging technologies that are just a little bit behind on adoption, but maybe it could fit into this as well. So if we think about heat pumps, so basically using electricity to not create heat directly, but to create heat in internal spaces. Electrolyzers, where we take electricity and turn water into its components, into oxygen and hydrogen. And direct air capture, we take CO2 and take it out of the atmosphere and concentrate it and do something else with it. So that's another set of technology that could play a role. Then there's these other technologies like nuclear fission, like carbon capture, and then solar radiation management, where we would block sunlight on purpose to do some cooling that way. And then for all these technologies, general purpose technologies have played a role in the past, and one that's kind of moving kind of quickly. It's just digitalization, and a lot of people have done work on how information and communication has the potential to change how cities work and how energy use works in cities, for example, and how that maybe has climate benefits. Using data and making decisions autonomously, like with AI, has a potential, and then synthetic biology has a potential to make some of these changes as well. So we can think of a bunch of technologies here, and then think, are these dynamic? And I think here's where we just try to collect some preliminary data on all of these, but the top row for sure is dynamic. That's really taking the data that I showed a few slides ago. The second one on emerging technologies also looks dynamic. Heat pumps are getting adopted. They're falling in cost. Electrolyzers seem to be falling in cost as well. And then direct air capture, we'll see about that, but there's potential for it to get to fall in cost as well. And then it's hard to say that nuclear power is a dynamic technology. It doesn't look like it's not getting adopted very quickly. It's not falling in cost, and it's not improving in efficiency, for example. So there's certainly progress happening in science and research on nuclear and proposals for new designs, and maybe even doing smaller scale designs. But so far, that does not seem like we would call nuclear a dynamic technology. Carbon capture, okay, you can see from this slide that it's getting adopted, but that's 50 years, probably 40 years of active adoption, and we're only up to about 24 carbon capture plants in the world. Most of those are industrial facilities. There's only one electricity generation power plant that has carbon capture on it, and that's in Canada. And so that doesn't look like a dynamic technology either. And then solar radiation management, so far it's just an idea and hasn't been even tested outdoors. And so that's something that we wouldn't say is dynamic as well. But these general purpose technologies are certainly dynamic. The improvements in microprocessor speed and the cost of accessing information, improvements in artificial intelligence, and then synthetic biology and gene sequencing are rapidly changing as well. And so those you would think could play an important role here too. So, and then there's wild cards I'll put up here too about like nuclear fusion or general purpose technology like superconductors or quantum computing. So those could play a role as well, but still hard to tell when they would be available for use. So it could be that this set of technologies I showed in the slides before, especially the dynamic ones, could do a lot of the work, could do maybe like the slide from that UC Berkeley study for US electricity in 2035 had 90% of the work. And maybe for globally in 2050 to 2060, maybe we get to some number similar to that. So we may need other technologies for certain roles, but most of it could be done by these rapidly changing technologies. But that doesn't happen without policy support. And that's the kind of the focus that I'm starting to work on next with this work. And I think I mentioned all these reasons why policy is needed, and those still play a role even as the technologies mature and become rapidly changing and dynamic. So there's this pollution externality, there's knowledge spillovers. So once you invent a technology, there's a lot of incentives to just free ride on other people's investments. And so maybe we don't have enough investment. There's innovation systems that maybe not functioning. We might need policy to support collaboration or exchange or create markets, that type of thing. And then also that we need it for inclusion and thinking that people benefit from the system as well. So those are the reasons. I won't say too much about this one other than there's been this broad evolution, I think I could say, in environmental and climate policy from thinking more broadly about the problem, from originally thinking about it as a pollution problem that really just needed a carbon price. And we had an example of that from how we dealt with acid rain with permit trading in the 1990s, for example. And then in the 2000s, we start to broaden the policy tools because we start to emphasize this knowledge spillover market failure. And then in the 2010s, the innovation systems work starts to focus on innovation systems as being something we need to do. And then there we have to focus a bit more on demand, and maybe carbon price plays a role, but maybe not completely. And then the last few years, there's really, I would say the two additional goals that we put on there are the distributional concerns and equity, and also the urgency. And it's interesting that we have to think of how do we do it in a way that both of those can occur. And I think for most people that work on this, it kind of seems like you really can't sustain a speedy transition without really focusing on the equity part as well. And so social policy becomes an inherent part of climate policy and part of environmental policy. And so the Green Deal in Europe and the Green New Deal in the US are kind of examples of that. So that kind of shows this broader set of emphasis over time. Yeah, and so I guess, I'll just put on two more slides here. So if we do have this kind of focus on dynamic technologies and thinking about how we support them in a more comprehensive way, there really are some risks. And I think these are ones we have to be serious about as well. So first of all, we might think about firms that try to influence the direction of the policy by rent seeking. And so that's something we have to think about. That's always been there, but now it's maybe different firms. Maybe it's now the green firms, the clean energy firms that would play a role there. And so that could distort the directions we go. So that has to be managed. The other thing is that, doing some of these policies, they're not just about kind of treating every technological opportunity with the same incentive. There might have to be some selection. So for example, if we're thinking about funding a demonstration project, that governments actually have to pick. And there's this concern about whether markets should pick winners or whether government should pick winners. And that's often used to say that markets are always smarter than that. But there could be really reasons why we might want governments to do some picking, but to make good choices, you need good information, good people to make good decisions. So that's a challenge too. And a lot of that has to do with information that governments have if they're going to play a role here. And And we have to think about issues where what the governments do might just take away from what the private sector would have done. So governments might need to get smart about picking their spots and not investing in areas that the private sector could do it, and kind of focus resources on places that the private sector would not. And then also that there might be risk aversion in the public sector. And I think there's a fair amount of evidence that that can play a role. And like I said, with the policy experimentation part here, we want some failures, we want some iteration, we want some taking risks to see what works in terms of technology and policy and different types of efforts. So we want to make sure that people are not punished for their particular choices not working out. Okay, so I'll just finish up on this slide, which is really just to summarize what I said at the beginning. So major progress in low carbon technologies. It also seems like there's something to small unit size. It seems to get adopted more quickly and fall in costs more quickly. And thus, maybe there's a way that smaller technologies are actually more scalable than large ones. Because of that first point, the low carbon transition is now more feasible and affordable. We actually have governments saying they're committing and planning to peak emissions to rapidly decline, and that's now realistic, and that some of these technologies that I've talked about can do much of the work, but that we still need policy for these multiple reasons, that we need models that are up to date and that talk about reality, not what's happened in the past, because the faster that things are changing, technologies are changing, other conditions are changing, the more up-to-date models need to be, and that in the end, policy needs to anticipate and not think about what was true in the past. And so we should design policy with these technology dynamics in mind, and we need a more comprehensive mix of policies that some people might call industrial policy, but a lot of what to make that work well needs to be implemented well, and that means we need capacity in government of good information, smart people, probably more people making more decisions, and that's something we need to change as well. So I'll stop there, and yeah, thanks for the chance to present my kind of emerging research here.
Great, thank you.
Thank you. I think we can, like, if everybody can turn on their camera so we can go to the Q&A session. I will appreciate that.
It's nicer. All right, so who has questions? You can either raise your actual real hand, or you can try the raising the chat, the Zoom hand. Sometimes it's hard to see. Jump in, go ahead, Pedro.
Hi, Gregory. Thank you so much for the talk. I think it's awesome. My question is simply, how us as students and scientists, what's our role in this and pushing this policy, and what's our role more in how could we more effectively help the policies? Seems like policy is something that is sounds like very political, or sounds like very activist, but I'm not sure how we as scientists can help push that.
Yeah, that's a good question. I mean, I usually just say three things. I think it's like a personal question too about where you fit in. But first thing is people voting makes a difference, and young people don't vote very much, and that's explains a lot of what we prioritize in this country. And so I would say that's an important thing to make sure that you tell other people to do. Yeah, and a second thing I would think about doing is using your talents, especially as whatever you're working on, and thinking about how that could play a role in making policies feasible, whether it's some new wind technology or a way of integrating wind into the grid or something like that. Like, these technical improvements really do make some of these policies more feasible. Like, we've had a hard time passing a carbon price in the US over the last, since the Clinton administration. It's a long time, but it's probably more realistic that we could do one with these technologies that allow that price not to be that high to still play a role. So there are ways that your work, either as a scientist and engineer, can play a role in enabling policy. And then I think there's a communication aspect as well about getting smart on these issues, talking to other people, and maybe even talking to people that run for office or might run for office, and maybe putting this these topics on their radar screen. So I think, yeah, that's a good question. I'm glad you're asking that. It makes me encouraged to think about wanting how to act.
That's great, if I can, I mean, I think that's really great. And I do think, yeah, public engagement. So the work that all the work that we're doing is either around energy. I mean, Pedro's kind of on both sides. He's a geoscientist, actually. So it's kind of related both to the impacts of climate change and things like hurricanes, but also thinking about hydropower. But I think for all of us is partly to remember this public engagement, that we're doing this really cool stuff. And if we can figure out a way to communicate it with the public, that, you know, it all helps to kind of get policies to go forward. So
yeah,
that's a great question.
Right. Yeah.
Who else has a question?
I have a question.
Yeah.
Is about the figure that you showed before of the learning rates. I just want to make sure that if you called, I don't know if you can share that figure.
Sure. Yeah. Let me see. This one?
Yeah, so you're calling over there learning rate, the ratio of final to initial cost associated with a doubling, right?
Mhm.
Of a commit. Okay, it's okay. I just call that progress ratio because it got confusing because I usually call the learning rate like because I was just looking actually the definition, because usually people call that like the proportional cost saving made for a doubling. So I was expecting like the opposite behavior, but that's fine. I just want to clarify that. It's okay.
Yeah, I think at least that's the way I use it, is a learning rate is this, that the progress ratio is 1 minus the learning rate. So that, yeah, like this central about 20% would be 80% for progress ratio. So that it's a 20% reduction. Yeah, it's 80% of the cost if you double.
Okay. Yeah, that's fine. That's fine.
Yeah, cool. Well, good that you're deep on learning rates. I think that's because it's something that, you know, that's been around for a long time, but now people are kind of, I don't know, like using it because it seems to come up quite a bit and explain quite a bit. So
I use it myself. So
okay.
All right, Anna, looks like Anna's got
Anna. Yeah.
Hi, can you guys hear me okay?
Yeah.
Okay, thanks so much, Greg, for the talk. Sorry, I'm out in the world. I was wondering about that same figure that Chris asked about. So when we're thinking about size as an important factor, what about the other factors? I'd love to hear your thoughts on like Laura and Kavita's work on wind and international supply chains, and then, you know, various things about complexity of supply chain that relates to size but is slightly distinct from it. So how do you process all those sort of multi-factor issues?
Yeah, I mean, I guess, yeah, the first thing I start with is the R squared on this one is similar to that one I showed in the other one. So it's like 80% of the variation is something else besides unit scale. So yeah, I mean, I think all I have now is a list, and I talk to people about, you know, what else do they think would explain it. So yeah, maybe something about complexity of the device, how many parts there are. Other people have talked about how much material is consumed in the device. So the more material there is, the less opportunity there is to improve and learn. So with solar, it's really just about the surface that matters. So it doesn't really have to be much material at all. And similar with a battery too. I mean, it's like a surface that's wrapped up in a coil, but it's still, you know, not a ton of material. Whereas other technologies, we're actually talking about, you know, building a lot of steel or concrete and need to protect itself, and maybe wind is kind of in the middle that way. So material consumption, that seems to be one. What else did we talk about? Like how much customization needs to happen, or can you just sell or make the same thing and everyone can use it in exactly the same way? So that's another part of it too. How competitive it is. So maybe there's a difference between price and cost that way. So yeah, there's a bunch of factors. And so, you know, people are starting to look at different factors and how they play a role. And if you had a big enough data set, maybe you could start to put all the factors together and see which ones seem to play a bigger explanatory role than others. So yeah, that's important, and a direction to go about what are the other factors too.
Thank you. All right,
I think
Dora?
Dora has a question. Yeah. And Greg, I think you can stop sharing your screen so everybody can
Okay.
see each other. Yeah.
Thanks.
Yeah, thank you so much for the talk. This was really interesting. I was also thinking about the trend of smaller scale technologies developing faster in relation to wind, since that's like my area of study. And it seems like in the last 10 years, like especially for offshore wind, there's sort of been an opposite trend where like the prices seem to be coming down because turbines are getting bigger. Or I mean, that's one of the reasons, and turbines like continue to get bigger. I don't know. I was just like wondering if like if you know of like the complicating factors, I guess, that change that
Yeah.
trend for wind. Or
Yeah, absolutely. So that's, that's one thing that the learning curve does, is it, combines all of these different factors. And some of them are about kind of repetition and iteration that I kind of emphasize with that number of iterations slide. But there's also economies of scale. And if you look at the wind learning curve, as you say, especially more recently for offshore wind, a lot of that's been driven by larger and larger turbines. Yeah. And so that you get, I don't know, yeah, like the square of the area, but you're only increasing the length of the blade. And so there's real gains to that. And so, yeah, that's certainly part of it as well. There's economies of scale. And yeah, I think you have to think about, where economies of scale are the real opportunity, and where kind of iteration and modularity is the opportunity. Now, one place I think that really interestingly coming up is in direct air capture. That's where you absorb CO2 that's already in the air and remove it. And that could be a net negative emissions technologies. And there's only 2 companies in the world that are actually building those machines. And one is doing an approach that's purely on economies of scale, trying to make it basically the size of a coal power plant, like 1 million or 2 million tons of CO2 per year in reverse. And the other is doing like shipping container size. And there it's all about modularity and kind of solar battery style learning curve. And, it'd be interesting to see how they both play out. But one is purely on economies of scale and the other one's purely on modularity.
That's super. That's what I wanted to ask. I was like,
Okay.
that's so interesting, because that's exactly, and so you're not necessarily betting on it. I mean, it sounded like from your talk, you'd be betting on the container ship size one.
Yeah,
But so far, is all the data proprietary right now? So do we not actually have any idea where they're going, or what's
we kind of know where they're going. Like one is really trying to do big and the other's trying to do small.
No,
but in terms of like costs, yeah, that part, yeah, we don't know.
You don't have any costs yet to know if either one is heading in the right direction.
Yeah, no, we don't. I mean, there's lots of people that have kind of made studies to estimate where there would be. I think the one, so you're right. Like I've kind of found it much more credible to think about the small scale actually getting somewhere. But the part about the large scale, as I've talked to them and learned a bit more, they're trying to do modularity within their large scale. So one plant is big, but they have many units, like a contactor. They'll have like 200 contactors, and they think they'll get economies of unit scale and production and learning by doing that part. But then they say, some parts don't make sense to do small, and so we're just going to do them big. So yeah, it's a combination, but yeah, interesting to see kind of the really different different paradigms on how you get this thing to actually work and become affordable.
Yeah, and I wonder how the dynamics of the policy and the market work with those two as well, right? Because direct air capture right now doesn't have a lot of value. I mean, I guess there's a little bit of value on a ton of carbon, right? But you really need policy, some serious policy to make that work. And so it'd be interesting to think about, if you don't have a market, and you're not quite sure when your market's going to arrive, again, are you better off with the small little thing, or are you better? I mean, I don't know, but it's interesting because it's an interesting, odd dynamic. I mean, I don't know. Have we had tech? I mean, do you know actually? So do we have technologies that have no value in the absence of policy? Any other ones besides direct air capture? I mean, I guess carbon capture has some, but.
Yeah, I don't know. I mean, beyond energy, like I guess maybe like military defense and things like that, where you really need policy to say that there's a role for it.
Like solar, I suppose. So solar didn't have any real value, maybe I mean, I don't know. Yeah, anyway.
Well, but I think that is an important distinction, is that, solar or electric vehicles or wind, there's always this potential that you could get below the cost of the alternative, below
Right,
natural
right.
gas or whatever it is. And then you don't need policy anymore. And
Right.
actually, if you keep going down the learning curve below it, you're actually paying back in kind of some broad social way all the policies that happened before. But yeah, you don't have that with direct air capture. There's no like target where you don't need policy anymore because it's cheap enough.
Right.
Because it's only purely public good. There's really, yeah, so that's different. So I think you have to think about the policy implications of that part of there not being a long-term market without policy. But also as your first part of the question, yeah, like, do you need different policies for small scale versus large scale? And in that case, they're like really different. So yeah.
Interesting. Any other questions?
Yeah.
I can always ask more, but I see Greg all the time though. So
Yeah. Any other?
else? Oh, there we have
Pedro.
Pedro again.
Yeah, sorry. And I was wondering, like, you mentioned about the how the cost would be reduced by different collaborations between different countries and doing most of it doing RD, if I'm correct. Which one do you think would be sort of like the actors? Is it like research in the universities? Is it research on companies? Is it research through government laboratories? And how do you think what's the best mix of it?
Yeah, that's a good question. I guess, well, first of all, I would say probably it's not just R&D that was kind of international. So the R&D played an important role in part, but that mostly in the early parts. And then later on, it was the, machines moving around and people, like someone who learned how to do manufacturing in Germany and then eventually became a consultant and worked on setting up solar factories in China, like that we saw as well. So yeah, it's not just the R&D part that's international. And then, but within the R&D, yeah, I mean, you've got those different institutions you mentioned, like a university, say a government laboratory, a private company. Yeah, they've got different types of objectives and different things they'd be good at. And, maybe one simple way to think about it is different stages. You might, like early on, it seems like universities probably are like kind of the place that would be kind of willing to work on things that don't have a near-term private return. Government labs maybe a little bit less able to do that, but more than private companies, and private companies that really need to justify their R&D to their shareholders. So there's kind of like the stages where you think over time, the private companies are kind of developing what they sometimes call absorptive capacity. So they're just working on this new direct air capture technology because they want to be smart enough to know which company to buy when it comes to that, or which technology to buy. And so they invest a little bit and have maybe a small team, but they're not doing their own research. And then as it gets more applied and closer to market, they might see they play a bigger role in it. So yeah, that's a good question to think about how these different types of institutions contribute.
That's interesting. So if you see, there's in the chat a question, which I don't know if you know or not, but when you were showing wind energy around 2010,
oh yeah,
there's a bump or whatever. So do you know what was going on there?
Yeah, so two things I would say on that. So one is everything started getting more expensive in the late 2000s. Actually, just like now, 2x4s have gotten really expensive. Solar is now more expensive this year than it was last year. Batteries too. So it's just kind of like when the economy is kind of having this boom period like it had in that period just before the global financial crisis, that makes inputs more expensive. And for wind, yeah, like as you guys know, there's a lot of important material inputs. And so steel and aluminum and concrete getting more expensive actually affects the installed cost. So part of it was that. But then there's also this other dynamic that I think explains a little bit about that, which is sometimes you can have costs get higher in the near term, but they create some longer term benefit later. And so, maybe as you upscale turbines around that time, there was a sense that they would bring the cost down because you get so much more electricity out of like just a little bit more material. But it was early investment, it was more expensive to do right away. So I think that's probably part of it as well. But yeah, it's interesting, and kind of as a researcher, it's kind of an interesting opportunity when things diverge from the learning curve. It might reveal something about what's actually going on and driving some of it, because when it goes the other way, for example.
I have another question about wind, but it is 5. So if anybody wants to sign
Okay.
up, they're welcome to sign up. And I'm just wondering, Greg, you said something that was a little different than what I understood. I thought that Margaret Taylor especially had said that the early wind policy in California was really, really poorly written policy. And then in fact, for a little while, wind got much more expensive because the policy caused people to not invest in improvements. I mean, so does that sound familiar to you, or am I
Oh,
missing
yeah.
something? Or,
Well,
okay.
she would know because
Yeah.
she studied that case a lot. And I guess, yeah, maybe, yeah, I'm trying to remember that now. I mean, the part that, so I don't remember the cost data on that in the 1980s that well. That could have been true. But the part I do really remember is the capacity factor going way up in that time and all the investment happening. So
there were
yeah,
improvements, but it just took a while for it to hit the cost, I think.
yeah, maybe that's it. Yeah. Yeah.
All right. Well, is anybody else? Although it is 5, so I guess we should. Anybody else have one last question? All right. Well, thank you, Greg, very much. We appreciate
Thank
that.
you.
Very
Yeah.
nice. So thank you very much. And hopefully someday, maybe in a few years, we'll get you back on campus and in person.
Very much would like to. Yeah. Thanks, Erin, for having me. And thanks all of you for your questions. Great to talk to you today. So, all right.
Thank you.
Bye.
Yeah.